So next we're going to have Tom Caputi talking to us about a very exciting feature, which is native encryption in ZFS.
Hi, everybody. I'm Tom Caputi, and today I'm going to be talking about something I've been working on for the last 9 months or so, which is basically adding encryption at rest into ZFS. So basically, I'm going to start out with an overview of the implementation of, what you're going to see as a user, what you can kind of expect from, a sysadmin's point of view, and then I'm going to kind of build up the encryption implementation as we go through the presentation so you can kind of get an idea of how it works at the block level. So first of all, what is encryption? From a really basic 40,000-foot view. Basically, we want to prevent somebody, known as the attacker, we want to prevent them from accessing data that belongs to us, data that we're considering private. Permissions are not good enough to protect against this because no matter what, a root user can always change the permissions on pretty much anybody's stuff. So if you have files or directories, if you don't trust the root user on your system, you can't really do anything to protect your data from them. Kernel bugs have routinely been exposed in Linux, especially in the past couple of months, where there are kernel bugs that have allowed for privilege escalation, which allows other, untrusted users to get to root, and then from there they can access your data. So this really isn't good enough. And the other thing is, even if your data is in some machine and you know that nobody's going to be able to escalate, and maybe you are root on your machine, somebody can always move the disks to a different machine or install a new operating system, and they'll be able to read the disks no matter what. So really, permissions are not good enough to protect against these kinds of things. The solution is going to be to encrypt the data. And what that means is that the data that's on disk should look pseudo-random to everybody except somebody who has the private secret key. The user basically is going to be able to encrypt and decrypt data with that key in order to get to it and access it as they want to. But from an attacker's point of view, if you don't have that key, mathematically it's going to be very hard to decrypt the data or even to write new data. So let's talk about why we want to do encryption in ZFS now, as opposed to above it or below it. Let's talk about above it first of all. There's a couple of solutions that deal with this. One of the big ones that comes to mind is EcryptFS. One of the biggest issues with this from a performance standpoint is that ZFS is able to get a lot of performance out of the fact that it compresses data before it goes to disk. If you have encryption on, remember your data is going to look pseudo-random. So in pseudo-random data, there's no patterns there. There's nothing really there's no compression that can really be applied to it. So you will lose a good amount of performance there. You also lose dedupe capabilities because if your data truly is pseudo-random, two pieces of data that might even be the same are going to look completely different. The other thing is that it's going to write out metadata headers and stuff because encryption, as I'm going to show you in a little bit, does require having some metadata that needs to move along with the data. These in EcryptFS and a few of these other solutions are going to be written in a header in the file, which can basically disturb the file alignment, and therefore things like databases might not perform as well. Now, that being said, there's even more restrictions if you do encryption at the disk level. At the disk level, let's say you have some kind of RAID system set up, and then you have a dencrypt, for those of you who use Linux, set up on top of that. Basically, if you have multiple copies of any data, that's going to be encrypted multiple times because, again, each block is going to get encrypted a different way each time. There's no intelligence there. And so that's going to mean extra CPU overhead for each encryption. The other thing is that you can't do any kind of ZFS commands. You can't even recognize that this is a ZFS pool until you've loaded your keys and got the underlying block device decrypted. So what this kind of means from a user's perspective is that you're going to have the keys loaded all the time. I mean, because if you want to use the data, they have to be there. This will also mean that if the keys aren't there, you can't do basic pool operations like scrub, resilver, nothing like that. You also can't send data without having the keys loaded. And the last big advantage of disadvantage of both of these things is that it kind of adds more complex management, because right now you can manage all of your storage through the ZFS and zpool commands if you're using ZFS. But with this, you need to add another layer which will just handle the encryption either above or below. So this is kind of a big win just from an administrative standpoint. So for those of you who don't know, I thought I'd include a little slide on how we're planning on using this at Datto. Basically, Datto, to sum up one of our biggest products in a nutshell, it's basically we have a backup agent, which is a piece of software that lives on a client's machine. The clients are going to back up their data to a zpool, which sits on a separate machine on site at their office or wherever it may be. And then that is going to back up to the cloud using ZFS send. The advantages of native encryption here are going to be that we're going to be able to get a lot higher performance encryption without losing compression because it is baked into ZFS. We're going to have a much cleaner implementation than we currently do because what we currently have is a bunch of stacked block devices that perform the encryption intermediately. And the last thing is that we're going to be able to back up our customers' data to our offsite server without being able to decrypt it, which, from our users' perspective, they're going to want that because they don't know if they can trust us necessarily, and we also don't want the liability of being able to decrypt it. So now let's get into what is actually going to be encrypted in a ZFS encrypted volume or in a ZFS encrypted pool. Basically, all of the user data. File data and metadata will all be encrypted. That includes ACLs, names, permissions, attributes, all of that. Directory listings, all of that. ZVol data, FUID mappings, master keys, which I'll get into in a little bit about how that works, but your master keys are actually going to live on disk, but they will be encrypted separately. All of the above will also be encrypted if it lives in the L2 ARC, because that is still persistent, even though most of the code kind of assumes that it's, that once you reboot, it's gone forever. But with encryption, we really can't assume that. And then the other thing is all of that will still be encrypted if it's in the ZIL. What's not going to be encrypted is basically anything that's related to the structure of your pool. So dataset, snapshots, and names, anything that lives in the MOS, pretty much. Dataset properties, the pool layout, structure, the dedupe tables. So the dedupe tables will be clear and unencrypted, but the data itself will actually be encrypted, for those of you wondering. And everything in RAM will not be encrypted either. To give you an idea of what this is going to look like from a sysadmin's point of view, these are going to be kind of the new commands that are going to exist. There's a modification that's been made to ZFS create that will allow you to add 2 new properties. One is encryption, which is basically your encryption algorithm, and I'll get into what we're going to support for those of you people who know encryption fairly well. And the other one's a key source, and the key source is basically just how you're going to provide your key, your password, your hex key, your raw key, however it may be, to ZFS. Along with that, we have a new subcommand ZFS key, which will help you manage your keys in ZFS so that you can decrypt and encrypt and decrypt your data. Basically, there's going to be ZFS key-L, which will load your key into the system, allowing you to encrypt and decrypt anything that's there. -U will unload the key, basically doing the opposite. -C will allow you to change your key so that you can change your password, change your key if you feel like it may have been compromised, or just want the security of being able to rotate it, and that will not re-encrypt all of your data, by the way. The other one, there have also been modifications made to a number of ZFS and zpool commands so that you can load the keys as you're mounting and unmounting things. The key things to remember here is that as long as the key is loaded, your data sets will be mountable. So they'll be able to be brought up, and they'll look just like normal ZFS file systems to everything else. Your child data sets are going to inherit encryption properties and the key source by default. You can also set new encryption and new key source stuff and new key sources on child data sets, and then they'll kind of be encrypted and need to be mounted separately. And as I said before, the key and key source will be changeable without having to re-encrypt the data set, but it will still be secure. Last thing to talk about as far as administration is basically what we're going to support as far as encryption algorithms right out of the gate. The first one is we're going to be supporting AES as our main block cipher, and I'll get into what that means in a minute, in CCM and GCM modes, and with 128-bit, 192-bit, and 256-bit key lengths. Encryption equals on if you just take the default on it. Encryption will default to off, but if you say encryption equals on, that will default to AES CCM 256-bit. The key sources, which again is how you're going to give your key. You can either specify that you want to do it from a prompt. So basically, when you say ZFS mount or ZFS key -L or one of those other kinds of commands, it will prompt you for your key at the command line. There's also a file. So if you want to have your key in a separate flash drive and you plug it into the flash drive, and then then your data sets are mountable, you can do that too for greater automation. As far as the formats, you can give the key either in raw bits, just as it actually is, in hex, or a passphrase. If you do specify a passphrase, we're going to have variable numbers of PBKDF2 iterations, and I'll explain what PBKDF2 is, but for those of you who know encryption, that will be important. And we also have these new properties, which are encryption, key source, key status, and PBKDF2 iterators, which will kind of become self-explanatory in a minute. So as far as the things that kind of had to, some things that had to change that aren't necessarily the best as far as ZFS encryption goes, the biggest compromise we had to make was that copies is going to have to be limited to 2. So you won't be able to do copies equal 3 with your encrypted data. Dedupe tables themselves, like I said, are not encrypted, but that being said, the data that is in a dedupe table is encrypted. But what this means is that you'll be able to still see some patterns in your data. Within an encrypted data set, you're going to be able to see which blocks have deduped against each other. The last thing is kind of, I encourage people to Wikipedia it if they're interested, but basically there's something called a crime attack that is not applicable to 99% of applications. It can be, if you're really concerned about it, you can get around it with compression just by turning compression off, but for most applications this won't really matter, so we're not making it mutually exclusive. So now I'm going to kind of show you and walk you through the implementation of how the actual data gets encrypted on disk, and I'm going to kind of start from the ground up. So what I mean by that is, first we're going to start off by talking about the encryption scope. What is actually going to be encrypted? Obviously, it's going to be the user's data, but are we going to do it at the file level or the block level? We're going to be doing it at the block level, and this is going to be for a number of reasons. First of all, we're going to be able to encrypt each block separately, which means that if you have a very, very large file, in order to encrypt or decrypt anything, you need to encrypt and decrypt in that unit. So this will kind of limit it to the maximum block size. So if your maximum block size is 128K, the most you will ever have to encrypt and decrypt at once is 128K. We're going to store the encryption parameters in block pointer T, and that's going to be important in a little bit, and I'm going to show you how that's all going to work. By limiting the scope of the encryption to a block instead of to a file, we can make sure that only blocks can get lost, due to loss of encryption parameters, things like that. The scope for that is only a single block as opposed to an entire file. So now the two types of encryption, and again, this is from kind of a 40,000-foot view, is asymmetric encryption and symmetric encryption. Asymmetric encryption, just for completeness, is kind of like the kind of encryption that's done for SSH and TLS handshakes. It's meant for verifying people and verifying trust between users and making sure that everybody who's talking is who they say they are and that they trust them. This is very slow. And usually what happens immediately after this is they exchange a symmetric encryption key. A symmetric encryption key uses a single key for both encryption and decryption, whereas an asymmetric encryption has a private and public key pair. Now, this is going to be way, way faster than doing asymmetric encryption for everything. On an x86-64 architecture, if you have the AES-NI instruction set, which if you're using an Intel processor, you probably do, it will actually be just about 1,000 times faster to do this encryption and decryption than it would be if we were trying to encrypt everything with RSA or some similar algorithm like that. So let's start off by talking about the basic unit of encryption. This is called a block cipher. A block cipher essentially takes one block of plain data and your encryption key and will turn it into one block of output data. Now this is good, and this is what we're going to be basing everything off of, but this has a number of really severe limitations, the biggest of which is that it only works on a fixed block size, which is 128 bits. Most of us want to encrypt more than 16 bytes of data. So we're going to need to modify this, and we're going to need to turn it into a stream cipher. What a stream cipher is, basically, is we're going to take, the most basic stream cipher is called ECB mode, or electronic cookbook mode. And what that's basically going to do, or electronic codebook, excuse me. But anyway, what's going to happen is basically we're just going to take the AES algorithm on each block of the plain data and kind of just do it in series on each single block. So that's going to actually encrypt all of our data, and we can now encrypt as much as we want, but this has a severe problem too. For those of you who've studied cryptography a little bit, this is kind of the picture that everybody knows and sees, and it kind of explains the big problem with ECB encryption. The problem is that you can still see patterns in your data because everything was encrypted the same. Everything was kind of encrypted the same way. So each block, you can still see patterns in all the data. What we want really is this. Is pseudo-random data. We don't want to be able to detect any patterns. Everything should be, completely random. So in order to combat this, we're going to make this a confidential stream cipher. And what a confidential stream cipher means is that basically we're going to add in this thing called an IV. The IV kind of acts as a salt for the AES algorithm. So the first block is going to be encrypted, salted with this IV. And then every block after that is going to take kind of the result of the last block and use that for the next block. So that this way, we can't detect any patterns because every block is kind of dependent on the block before it. This is going to be important for a number of reasons. The big thing is that there's a bunch of different ways to do this, and these are called modes of operation. And each one is going to have some slightly different requirements for how we need to manage it. Basically, the big requirements that you need to know about in order to get the rest of this presentation are that we're limited to up to 104 bits or 13 bytes. That's the maximum size that we can allow of an IV for the two modes that we're going to be supporting. And 96 bits or 12 bytes is what's recommended by NIST because of a number of performance issues. The other really important thing is that reusing an IV with the same key will result in a catastrophic failure of the encryption, which basically means that even if you don't have the key, you can decrypt both blocks of the data. This is really, really bad, and it means that we're lying to the people who we told them that we encrypted their data. So obviously, we don't want to do that. So the big things to take away from here are the IV needs to always be unique for these two modes, and we get 12 bytes of it. The last thing that we want to add to this kind of basic block of encryption is what's called an authenticated encryption. Now what this means basically is once we've written our encrypted data out, how do we know that nobody's changed it when we go to decrypt it? We want to make sure that what we wrote out is exactly what we're reading is exactly what we wrote out, and that because with a regular like SHA-256 checksum or any other kind of checksum, anybody can produce that checksum. And if you can change the ciphertext, you can get our applications to decode garbage, and that's still not good. We still want to be able to make sure that our data is secure. We at least want to know that somebody was trying to alter our data. So we're going to add something called a MAC. A MAC is basically a message authentication code, and it's basically a checksum, a cryptographically secure checksum like SHA-256 or SHA-512 or one of the other ones. That will require a secret key to produce. So in this case, that's also going to be the encryption key. We're going to So basically, when we go to decrypt this data, we can check that the MAC against what we actually had, the resulting MAC from decryption against what we actually had, and we can make sure that since nobody else had our secret key, if the MAC doesn't match up exactly, then this won't work, then we know that somebody tried to alter the data. So the next thing that we want to add in here is if you look at this encryption key. If you remember before, I was talking about the IV, and what I said is that the IV is limited to 12 bytes. 12 bytes is a lot of room for data, but here at ZFS, we promise to be able to store up to a zettabyte, theoretically, of data. So we need to be able to use more IVs without the risk of reusing one. So what we're going to add is this HKDF function. An HKDF function is really simple. All it does is it takes a master key and then a salt, which we're going to store somewhere too. And the salts, between the two of them, they will basically result in an encryption key. And this encryption key will be what's actually used to encrypt the data. We can generate a new salt every once in a while. And what that'll enable us to do is it will give us basically a fresh IV space, and we don't need to worry about colliding with previous IVs that we might have had before. This is relatively quick to calculate, and it's basically, like I said, the whole point of it is to prevent the master key from kind of going stale because we're running out of IVs that we can use. Now, that being said, this salt and this resulting encryption key are going to be usable for quite a while. So we don't need to change it on every single operation. So we're going to be able to cache this for a while. And basically, we will regenerate it every certain number of transaction groups or every time that you re-import the pool. I'll get back to you at the end. So now this is what our diagram looks like. If you notice, we replaced the regular encryption key, and everything here that's highlighted in red is stuff that we added to it, basically. And now we have our master key, which is going to be used with a salt to produce the actual encryption key. And then that's what's going to be used to encrypt the data. So now we have these two values right here, the salts and the IV. And the question is, where are we going to get these from? The answer is we're going to randomly generate them with a pseudo-random number generator. I can go over all the math if you guys really want to know about it, but basically, if you calculate out the numbers, what we're guaranteed pretty much is that we get whatever that number is, 41 million years. If we're encrypting 1 million blocks per second, we will have a 1 in a 1 billion chance of reusing the same IV with the same key in 41 million years. And by then, I'll be retired. So now this is our whole diagram. So if you look at the things that we have to store, I highlighted them in blue. They're basically the salt, the IV, and the MAC. The Cipher data is just going to go where the original plain data was going to go anyway, so we don't really need to care about that too much. It's just going to get applied to the transforms. So to talk about where these things are going to go, basically we kind of made a bit of a union out of block pointer. It's not a union in the code for those of you who might have been concerned about that, but basically we took a bunch of fields in the block pointer and started using them where we could. If you look at the salt is used for the fill count, is stored in the fill count. We can do this because the fill count, we only encrypt level 0 data, and level 0 data always has a fill count of 1. So we can assume that this is that this is 1 just because this block is encrypted. So therefore, we can store the salt there. We don't really need that field for these. For the MAC, we're going to store that in the checksum. It's basically going to be 128 bits long, which is half the checksum. And the reason that we can do this is because the MAC and the checksum kind of serve the same purpose. The MAC is there the checksum is there to make sure that data is exactly as we wrote it, and the MAC is the same thing, but it also protects against malicious users. There's two reasons why we split it in half and calculate both. The first one is because the maximum length of a MAC for both of these modes that we support is going to be 128 bits, so that kind of worked out. The other thing about it is that by having a half of a regular checksum, we'll still be able to do resilver and rescrub and all those kinds of and scrub operations just as you normally would by using that half of the checksum for checking all that, even without the keys loaded. The last thing is the IV, and Matt Ahrens and I talked about this for probably about a month and a half about where we were going to store this. We threw around a whole bunch of ideas. Basically, originally, to kind of sum it up, originally this was stored in the padding, which is right here, and that seems like a great idea until you realize that it would use 3/4 of the padding, and that would mean that we can't store any more uint64s in the future. So this kind of locks out block pointer pretty much forever. So we kind of didn't want to do that. We also toyed around with the idea of generating the IV from different fields in there. So, for instance, we could take the place on disk, but things get rewritten to the same place on disk most often. We could have added in the birth time, but the problem with adding in the birth transaction group is that ZFS, if you hard shut down, it can rewind a little bit because it will write out this block, but that won't be the block that's in the Uber block. So now we need to kind of have this count. So now we kind of it's not really secure. We can't really guarantee that is truly unique and that we never reused it. We thought about using the bookmark, but the bookmark gets complicated because when you have snapshots or dedupe turned on, that block could be referenced from multiple different places. So none of these were really going to work out. And so that's partially why it's randomly generated and partially why it's stored where it is. And this is, for those of you wondering from before, why we can't do more than 2 copies of encrypted data. You'll still be able to have more than 2 copies of the metadata above ZFS encrypted, but the data itself is limited to 2. So now let's talk about dedupe and how this will work with this, because we will still be able to dedupe. In order for dedupe to work, as it does currently without a whole lot of modification, basically we're going to need this MAC and checksum from back here to match, because that is the part that dedupe is going to look at. Now, in order for the MAC and checksum to match, we're going to need to write out the same ciphertext data, and in order to get that, or for equivalent blocks of data. And in order for that to work, we need to reuse the same IV and salt, otherwise we won't produce the same output. Now, if you've been listening to me this whole time, I've been saying, hey, we really can't use the same IV with the same key, and that's exactly what I'm proposing here. But the difference is that we're now also using the same data. And because we're using the same data here, what we've really only done is instead of leaking all of everything, we've actually just duplicated exactly what we had before, and we can use that to decrypt, and we can use that to detect deduplication. Now, this is technically still a leak of information because, again, we wanted completely pseudo-random that nobody can detect any patterns in. But the dedupe tables were going to leak this information anyway, and if dedupe is important to you, this is kind of something that you can be aware of and, and understand. Yes, this is only with dedupe, right. This is all considerations for dedupe, right. But your data won't be completely, entirely random, and that's something that you should kind of be aware of. If you're really concerned about it, you can simply turn dedupe off on those particular data sets. So how are we going to generate the same IV and salt for everything, for equivalent blocks of data? The only real way to do that is to take basically a checksum of the data. And because this is encryption, we're not going to take just a regular checksum of the data. We are going to take an HMAC. An HMAC is basically the same kind of thing as a MAC. It's a secure checksum that you need a secret key to regenerate. The only difference is that we don't also have to encrypt the data in order to make this happen. Basically, this is going to result in a 256-bit MAC, HMAC, and then that is going to be split up into 64 bits of the salt and 96 bits of the IV, and that's what's going to be stored. So now, this is where you get your money's worth. This is the picture of how encryption is going to work completely, basically. I highlighted the parts that are going to be different in red. So for non-dedupe, you're just going to have the plain data, and then you're going to have the pseudo-random number generator generating your salt and IV. For dedupe, it's just slightly more complicated. We're going to be using this HMAC function to generate your salt and IV. But that's really the only difference. Other than that, everything's going to work kind of the same. Nope. Basically, there's two last things to talk about as far as diagrams and encryption go, and actually getting data encrypted to disk. The first one is I said before that we don't want to have to re-encrypt all of the data that's on disk just because somebody might have compromised their password, or just because a user wants to rotate their password. That would be really, really inefficient. So we're going to add one layer of indirection between the master key that I was talking about before, which is right here, and between the actual key that the user gives you. So the user is going to supply this wrapping key, we're going to call it, and the wrapping key is going to be used to encrypt the master keys and the HMAC keys on disk.
You're going to want to PBKDF to that.
1 second. We're getting to that. Okay? Stay tuned. Now, this is what's, as this gentleman pointed out, basically, if you, this is going to be the case for when you have, for when you're specifying a key via raw or hex. So this is what it's going to look like. But basically, all we're doing is we're taking the master key, which we're randomly generating, and we're going to encrypt that on disk in a separate object, which is called a DSL crypto key. When it comes to passphrases present a slightly different problem. Passphrases are variable length, and they're reputedly extremely, extremely weak. You can come up with a table of like the top 1,000 most used passwords, and you can enter that into a data set, and chances are you might find something. You might find something. So what we're going to do to fight that is basically something called PBKDF2. PBKDF2 turns a passphrase into a usable key. So basically what's going to happen is we're going to run this function, and the function is designed to be just very, very hard to compute. It's going to take a whole bunch of iterations, basically, and the idea is it's going to generate out this key at the end of it. But if somebody were to try to do this over and over again, it would be very, very computationally expensive, and it would just take too long to actually do. For the person who's actually trying to decrypt their data correctly and is using the correct key, they only have to pay this price once, so it's not so bad. But anybody who's trying to brute force the password will have to pay this price many, many times. A couple of additional topics, just to kind of give you guys an idea of some of the things that are also coming with this. As far as ZIL encryption, ZIL blocks have a slightly, they need some slightly different considerations because ZIL blocks, first of all, are pre-allocated, and so we can't save encryption parameters into the block pointer after we've already written out the data block. So instead, we're going to have to do something a little different. First thing we're going to do is we're going to store the MAC in the ZIL header, and then the IV we're going to pre-allocate along with the block. I don't have a whole lot of time left, but basically the concept here, and I can talk to anybody who wants to know about it later, the concept here is that we're going to leave the ZIL structure intact, but encrypt all of the important user data in it. So all of the entries in it are going to be encrypted, but the blocks are going to be, but the blocks themselves and the pointers to other blocks within it are going to be left decrypted, which will allow the ZIL to be claimed without keys. L2 ARC encryption was changed a lot recently because of the compressed L2 ARC changes that just recently came out. But basically, the way that it's going to work now is we're going to, the idea of the new compressed ARC is that we're storing data exactly as it exists in the pool. So basically, when you read data into the L2 ARC, it will be compressed, but decrypted. And the reason for that is so that we can reuse the data over and over again without having to decrypt it all the time, because there's no real benefit to that. Once we have the data decrypted, or when we go to write it to the L2 ARC, we're going to re-encrypt it, and that's basically how it's going to work. But it's basically going to be exactly the same as it is on disk. And when it gets read off of the L2 ARC, it will use the block pointer T's, IV, and salt to decrypt it. The last thing is something that I'm kind of excited to talk about, and this is the idea of a raw send. So the idea is that we're going to, in addition to the compressed sends, which have just recently been merged, we're going to be able to take the data exactly as it is on disk and move it up to an offsite storage facility, even if it's untrusted, and it will be still encrypted. And basically the idea here is that you can send data to an untrusted server without risking that it can be decrypted. So this will make ZFS kind of a true platform for end-to-end encryption so that, we could really be used for anything, including high security security sensitive kinds of applications. An admin will always be able to take backups of their pool efficiently, even without the person behind the data being able to, or having to trust them, essentially. As far as the current status, this is completely implemented. Except for raw sends, that's going to be coming in a separate pull request. It's ready to review. I'm pleading for people to please review it and take a look and tell me what's wrong. Tell me, anything that you can think of that might be a problem with it. I've been kind of sick and tired of rebasing it on top of the current master for the past few months, so I'm definitely trying to get it pushed through. The primary pull request is on Linux, because that's where we at Datto are based, but there are pull requests out that are basically tracking the same changes on OS X and Illumos. I also wanted to give a quick thank you to Jorgen Lundman for helping to maintain the OS X and Illumos ports, and by helping, I mean doing it. Matt Ahrens and Brian Bellendorf, I'm going to guess, but basically for answering all of my questions about everything that's happened, and George Wilson and Dan Kimmel for helping me work through the ARC changes that just got merged in a couple weeks ago. Thank you.
I've got a lot of questions. I'll try to keep it to one most important one. Backing up the encrypted data, can that be done incrementally?
Yes, that will work with the same ZFS send stuff, because the entire structure of the pool will still, the question was, will send still be able to work with the data encrypted and still be able to do everything incrementally? The answer is yes, because the entire pool structure is still left unencrypted. And that's kind of a big win, because we can do that and we can do scrubs and sends.
I have a question about a couple of non-standard block pointers that data leaks. So you encrypt all level 0 data blocks, kind of thing, but doesn't that mean that so the presence or absence of a hole is unencrypted, which is, that's one of zeros, but then also embedded block pointers?
Embedded block pointers, you can't, this is not like a Z-pool. These features are incompatible, but at the ZIO layer, if you have encryption turned off, embedded gets turned off effectively, which is a bit of a performance loss for some applications, but that's kind of, I have to store the encryption parameters somewhere, so.
I had a couple questions about the master key.
Yes.
One was that if an attacker gets root on a running system, aren't they going to be able to extract that master key and use it regardless of whether or not you change the user passphrase?
The question is, will a root user on the system be able to get to the master key regardless, correct? As long as the system is running. The answer is the master key is never exposed to the users. It's completely kept within ZFS. And the keys, the wrapping keys aren't really exposed through that. The only way that they'd be able to get through that is through some kind of like dev mem and dev kmem interface that still exists on very, very old, very, very insecure systems. But that, I'm sorry? Or yeah, you could get it from a debugger, but most people, yeah. So one of the big things that I wanted to point out was that this is encryption at rest. This is kind of like encryption is broken into 3 different kind of categories: in transit, at rest, and in use. I can't really do much to protect encrypted data in use, because, for instance, that will even live in the page cache in Linux or Illumos or other things. So there's not a lot I can do there. This could be added, but this will definitely provide a big layer of security that will be very hard to overcome.
Would that also mean if you're replicating to an untrusted system on the remote end, you don't trust those people, they could be running a debugger on the remote end?
Yes, but you'd have to have also given them your key at the same time. because you would have had to enter your passphrase on the remote server. You can back the data up to there and be able to get it back, and yeah, and it will be able to be integrity checked, but it won't. You can't decrypt it unless you give them the passphrase as well.
With the tool running, it doesn't need the master key in memory?
No, yeah, exactly.
Awesome. Thank you.
You said a CCM or GCM?
Yes.
Are you aware of GCM's weaknesses?
Yes, it's there are weaknesses to everything, and people are finding different flaws in encryption algorithms. 128 bits. Yeah. There are weaknesses in everything, and every day people are finding more and more. Like I said, the default is 128.
I just brought up Neil Ferguson's 2005 paper about GCM's log weaknesses and said, don't use GCM, you have to use 128 bit.
There are a couple of things like that. We do default to CCM 256-bit with on, but this is also expandable. You can add, there's the possibility with this to add encryption algorithms, like as we find new ones, the same way we can add checksums.
Sorry, maybe this was entirely clear. So if you do a ZFS send of a data set that is encrypted, is what is sent unencrypted until the raw send stuff is in, and then the raw send allows you to send encrypted?
I'm sorry, could you repeat that one more time?
So if I have an encrypted data set and I do ZFS send, is what gets sent encrypted using the key, or is it the unencrypted version? And once you do the raw send work, then you can send it to the encrypted?
The question is, will the raw send the encrypted data as it exists on disk or the unencrypted data, correct? Or both, yeah. I think I have the answer. So tell me if this answers your question. Basically, I'm going to be adding a flag which will do a raw send, and if you have that turned on, it will be exactly as it is on disk. If you don't have that flag turned on, then it will just do a regular send, and you'll have to have the keys loaded just like it would normal. But that way you can.
Keys are not loaded, will then say it will still do the send, but it will be encrypted.
It will error out if you don't have the keys loaded normally, and if you do have the key, and if you don't have the keys loaded and you specify a raw send, it will do that. In the back. I can't hear you too well, but it sounds like you're just asking for performance information. We did some testing on performance, and basically what we found is approximately anywhere under a 5% CPU overhead. There wasn't a big overhead as far as throughput to disk is concerned, because that's kind of the bottleneck. But as far as CPU overhead, it could add as much as 5%. Usually we saw it at about 2.
Are you storing in the block pointer that the data is encrypted, and if so, what bits are you using to do that?
Are we storing that the fact that the data is encrypted in the block pointer? Yes, I believe it's bit 67. It is the one. It is the. There is. If you look in the comments of block pointer T, there's actually a bit that has been reserved for encryption since the Sun days, and I'm using that one.
Two questions. One, have you had any extensive crypto background into lawyer generation? And two, solutions like Lux, for if you wanted to use this for full disk and resolution offer multiple key slots. Are you going to do multiple key slots? And if so, are you going to tie it with EPM?
So the two questions were. Well, I'll answer the second one because I remember that. The second one was some systems like Lux have the ability to have multiple keys,
Yeah, multiple slots.
multiple slots to unlock the master keys. Currently, right now, no, but that could easily be added. The encryption keys are stored in a ZAP, so it'd be not too bad to add that functionality later in the future. But right now, it's just a single key to decrypt. What was your first question? I'm sorry.
Have you had anyone with extensive crypto background to make sure that all your protocols for key generation and crypto?
Have we had anybody with a extensive crypto background check all of the protocols and procedures that we're doing? Basically, the answer is not yet, but we're in the process of getting that done. And we've had people who are there's a big thing with anytime you work with cryptography, where anytime you ask somebody for their opinion, they say, "I'm not a cryptographer," but and then they give you their opinion. And we've hit a lot of that, but we're working to get that.
Surely you're using the internal crypto operators.
So for that, I didn't have time to cover this, but we're actually using Illumos's, which we have ported to OS X and Linux. The reason for that is because in order to we needed one crypto framework to kind of work across everything. So we made a separate module called the ICP, which will also support new checksums like SHA-512 and Skyne and a few other ones. That's actually out for another pull request right now. I'm sorry? The ICP is kind of like a framework, and I ported over the stuff that we needed for that, but if that exists in Illumos, then it can easily be brought in. Will do. How does this compare to the Oracle Solaris encryption? Basically, originally when I first started working on this, it was kind of based on it, but in the time that has happened since then, we found a couple of problems with it that I can get into offline if you want. But basically, we found a couple of minor flaws that we thought should be addressed. It's not compatible pool-wise at all, but that kind of wasn't a goal.
I just wanted to verify something on what I heard. So in the backup case and the full import case, all file names are leaked, that's correct?
All file names are encrypted in the... Are leaked? No, none of that is leaked. If you have an encrypted data set, any user information pretty much is fine, including file data, zvols, file names, ACLs, permissions, extended attributes, any of that, all encrypted. Yes, basically object data, and also the bonus buffer. For those of you who know about the DMU, there's a bonus buffer, and we force the bonus buffers for encrypted objects off to spill blocks, and then we encrypt the spill block. Right? Is it possible to list the snapshots without the encryption key? Yes, because that's all part of the pool structure. So the pool names will be the pool names and data set names that will not be encrypted, but everything within it will be. Do we have support for any kind of external encryption stuff? Not at the moment. And the reason for this is basically because OpenZFS needs to cater to OS X, Illumos, and OpenZFS at minimum, and it's very hard to kind of get those things to work across all three. It could be added in the future if we could figure out how to get a framework to work with hardware encryption devices. Is FreeBSD on my radar? I've just written the Linux version. I really want to thank Jorgen Lundman, and I'm hoping I'm pronouncing that name right because I've never actually talked to him. It's all been through emails. But he has been maintaining the Illumos and OS X ports. So that I don't, but it should not be incredibly hard to port at all. Is there a way to protect a USB key? If you have the passphrase on a USB key, is there a way to protect the USB keys stuff? There are plenty of ways to do that, including things like eCryptFS and other encryption things for that. That's kind of outside of ZFS. But the idea is that if you wanted to read it from a file, it was more going to be automated anyway, because if not, then you can use a password, just like normal, and I will be generating pretty much the same thing that the encryption key on the USB would be.
Common trick in Illumos is to use encrypted lofi in most cases.
You'll have to talk to me about that afterwards. Yeah.
Encrypted lofi for Illumos people is one way to do it.
Okay. Yeah. Oh, okay. Gotcha. Is there a way to list loaded keys? Yes, the key status property is a read-only property that will tell you if your key is loaded. Basically, the three states it can be in are dash, which means your data set is encrypted, available, and unavailable. Anything else? Thank you very much.